strategy is if the introduction is long enough, I don't need to say anything. I just move straight on to questions. The first question is, can we turn the lights down a little bit so that you can enjoy the slides a bit more? Great. Some of you may have noticed we put one more planet into the solar system in honor of Valentine's Day here. Okay. When we leave planet Earth, there are a whole lot of things that happen. There we are at NASA Ames. Actually, this was just last Wednesday, and those of you who have been to Ames recently but saw the hangar in its skeletal form, it is now recovered. And when we're at Ames or in this room, we don't have any trouble communicating. The words come out of my mouth and they virtually instantaneously hit your ears, and you can then block them if you wish. But at least they've gotten there in basically no time. But as we go off planet, suddenly we have a time lag in communication and certainly a physical lag. So there's a Landsat image of the San Francisco Bay to remind you where you are right now. There we are. And to remind you where NASA Ames is, we're your friends down south. I point that out because I once gave a lecture at Berkeley and they kept asking how my flight was. And I said, on the other side of the bay, they somehow thought I was from Ames, Iowa. Anyway, I'm sure no one here has that problem. Anyway, as you go even further into space, and here we are on the ISS, again, communication is virtually instantaneous, but it does take a little time to get crew up there and reload and so on. By the time you get to the moon, you've got about a 2.5-second delay in communication and a several-day delay in actually providing materials. And because I work for NASA, I get to be able to do this kind of thing. Here is an actual photograph from the surface of Mars, and I know Martin's seen this before, but for the rest of you, I'll give you a second to find planet Earth. And there we are. And we're now in a situation where communication, depending upon where the planets are in relation to each other, is somewhere between 4 and 20 minutes. And the actual time to get there with current technology is about 6 months. So now you really have quite a delay. And again, because I work at NASA and I can do this kind of thing, here's a photograph from Cassini. Obviously that's Saturn. And once again, I'll ask if you can find planet Earth.
Oh.
There you go. There we are, this little dot, and we're still in our own solar system, just to remind us how insignificant we are within our own galaxy, much less the universe. However, it doesn't matter whether we're in the rings of Saturn or Mars or back on the moon or planet Earth, we have certain needs as humans. One of them is transportation. The other is life support. We need food, we need oxygen, and I always like to point out that when I talk to people in the military, they say, oh, we work in really extreme environments. It's like, yeah, you get oxygen and gravity. We don't get those. Don't talk to me about extreme environments. We also need medicine, obviously waste recycling, clothing, and so on. We need habitats, which become even more important off planet with a higher radiation flux. We need power, we need heat, we need light. As I mentioned earlier in the day, there is no petrochemical industry off planet. And we need radiation protection, which again is even more important off planet. We need a form of communication, and just because this gentleman's waving a lot of dollar bills, I remind you, no bucks, no Buck Rogers. However, unlike the sort of constraints that we have on planet Earth, we have a totally different sort of constraint system that we're working towards off planet. And our big thing, at least has been traditionally, is up mass and up volume. It costs quite a bit to launch anything off Earth's gravity well. So we're talking about, for years, about $10,000 for a can of Coke. And then people say, what size can? You get the idea. It's expensive. Now, I realize that in this era of commercial space, some of the cost is going down. But as I pointed out last week, even if you were driving on vacation, filling up your car and going to Lassen, there is a limited amount of volume. So you still, at some point, have to make some decisions, what comes with you and what stays behind. So we've got the up mass and the up volume, which do get tied in very intimately, at least at this point, and probably forever, into cost. You also have to worry about storage, reliability, and flexibility. If you're at a building site here and the hammer breaks, so you run down to Home Depot or whatever and get a new one. You don't do that on the moon or Mars. You better have what you need with you or be able to repurpose something else. I used to say Amazon.com just doesn't deliver overnight to the moon, but it turns out that there are countries around the world, the audience says, they don't deliver overnight here either. So but they're very good about it at our house. Power, obviously, we don't have a power grid set up there, and again, to beat a dead horse, we don't have a petrochemical industry, or I guess to beat a dead dinosaur. So ultimately, you're dealing with self-sustainability, what I've started calling radical self-sustainability, because you not only know everything you've loaded into that spacecraft, and you know what your inputs are there, but you're now having to follow each carbon molecule, each atom of carbon, each atom of oxygen, each molecule of water. I've just been in a mining meeting for the last 3 days. There is basically no carbon on the surface of the moon. You are literally tracking every atom of carbon that you're bringing with you, because we are carbon-based compounds, our food is carbon-based, et cetera, all these biomaterials are carbon-based. So the question is there a technology that can help us? And we need to move, unfortunately for this, well beyond the technologies of the 19th and the 20th century, the era of big physics. And I believe, of course, that there is a technology that can help. And so I provided a black box with that technology for you. So the question is, what do I have in this black box? Well, this technology is programmable, just like your cell phone, so that's always a good start. And it's modular, which is handy because it gets into the flexibility. You can swap out modules, or at least tie that in with the programmability and add capabilities. And it's self-replicating. It's like, whoa, I don't know about you, but my cell phone does not self-replicate. In fact, I find that idea very, very scary. And it gets better than that. It's also self-repairing. Trust me, if I throw this on the ground, it will not repair itself by the end of my lecture, as I think all of us are well aware. So a technology that's self-replicating, programmable, modular, and self-repairing is already vastly superior to anything we have on planet Earth. And there are all these other capabilities that this technology has. And as you might imagine with this meeting, what I've just sold you, of course, in this black box, is life itself as a technology. And so once you realize that, you realize that there are all sorts of possibilities that you don't have from any other technology. So to summarize it, I think of life, when I'm not wearing my astrobiology evolution Darwin hat, it's a micro machine that does carbon chemistry and nanotechnology with exquisite precision. Wow, what can you do with that? And lots and lots. But then you add in this new field of synthetic biology. And there are all sorts of definitions out there. I just like this one in red, which is very stripped down, the design and construction of new biological functions and systems not found in nature. And that pretty much takes care of it. And if you want the cartoon version, that also pretty much takes care of it for you. So what's the big idea? What can we do with this idea of life as technology and providing an infrastructure for astronauts to go forward from planet Earth, particularly as we go to an era of exploration and ultimate settlement on the moon and Mars and who knows where else? Well, of course, I think that we should be using organisms for material production. And of course, this sheep is well aware, a nice Scottish sheep, that we use wool in our clothing. We have for centuries. In fact, we have for thousands of years. We've also used flax and cotton for thousands of years for clothing and leather. We've also used wood for houses and so on and so forth. So we use organisms and the materials that they make, their biomaterials, for our infrastructure, which is great. The problem is we're not taking trees, we're not taking sheep with us, we're not taking fields of cotton, we're not taking rubber trees. We might take silkworms, we might not. I have Japanese colleagues who have suggested that. And certainly not a tree like this that would provide us with lumber. So you think of that as a way to get cellulose. But of course, there are bacteria that also make cellulose. And so there's ways to make paper-thin sheets of nanocellulose So instead of a big tree, you're now dealing more like with a petri dish size, and those are pieces of cellulose that we've made in our lab over the years. And we could go on to how wonderful that is, but we shall move bravely forward instead. We are thinking, however, of taking this. This is a micrograph of a common soil bacterium called Bacillus subtilis. And you notice the little white dots it has? Those white dots are spores. It turns out when Bacillus subtilis forms a spore, it is incredibly resistant to space. In fact, these are our long duration space record holders for life on planet Earth. Some of these organisms were flown out of the long duration exposure facility. They weren't meant to stay for nearly 6 years. They stayed for nearly 6 years, and yet some of them were still alive when they came back to planet Earth. So these are incredibly resistant in the spore state. So as I always say, they don't have the personality of the protozoa and the algae, the things that I love, but gosh, they let you sleep at night when you're running a space experiment. So Bacillus subtilis all the way. Or maybe we'll take some of these. And what if we take these mushrooms or Bacillus subtilis and we engineer them with the capability to make silk or wool or cellulose or latex or precipitate silica or whatever? Why not take those capabilities that nature evolved and just put them in a different form factor and take them with us? And if we're not limited by form factor, maybe we can rearrange them. I mean, a tree is going to do its thing. Our bodies do our things. I don't know about the rest of you are parents, but I never once worried that my kids would be born with wings. Wasn't going to happen. We know what's going to happen, but what if we take the power to make something new with, say, these cells that are now engineered to make different materials? So what we've thought about for many years, and that's why I brought Jessica Snyder into the lab, because this has been her area of expertise from her thesis on, is to take a look at materials in nature. And many of them have their capabilities because they have a hierarchical structure. Our bones, for example, are not just a bag of cells. They have a structure from the nano level all the way to the macro, and that's what gives them their material properties. And so we can't just assume we're going to grow a bag of bone cells in a bioreactor and have a bone. But we could literally print them. And now if you're going to print a bone, why not make sheets of bone? And this is something that Jess and I have been talking about for years. Wouldn't it be cool if you had all those mechanical properties of a bone, but now you could make a sheet of it for the wall or whatever? And if the idea of habitats out of bone sounds weird, it's Back to the Future. This has already been done. But instead of worrying about finding mammoth bones, we could print bones exactly the way we wanted, with the right curvature and the right size. We've also thought a bit about the rachis, the middle part of feathers. I mean, how cool would that be to have sheets of some of these materials? So my grand vision off planet is to take something like a bioreactor of algae, something like that will provide the interface between the raw materials on the planet. So if you're on Mars, for example, carbon dioxide in the atmosphere and the water that's there and some of these minerals and so on, and convert these materials into organic materials. And I'm not talking about organic like in the organic section of Safeway. I'm talking about things like proteins and lipids and so on, organic molecules. And those can then be fed to something like Bacillus subtilis that maybe is going to be producing latex or wool or whatever, and then maybe Jess comes in and prints them into a sheet of bone or a sheet of feather or whatever, and you end up with really cool fabrics and filters and medical devices and maybe even balloons and drones and who knows what else. And so this is now engineering and rearranging nature to do unbelievable biomaterials. So let me give you some examples. One of them is habitats off planet. Here's a photograph from, I believe it was Apollo 11. And there's Buzz looking back at the LEM, the lunar module. Now, if you live in your habitat, you live in your spacecraft, it's reliable. It's what you came in, you don't have to worry about building it, and so on. But it wasn't very luxurious. So I did a calculation, and the volume inside the lunar module for Apollo 11 was the same volume as a C block cell at Alcatraz if it was only 5 feet high, and I'm even taller than 5 foot. So you're not talking about luxurious quarters for Neil and Buzz, but hey, if you're the first or the second or probably even the 50th person on the moon, you deal with it. But if you're expected to live there and work there and so on, you can't expect someone to be in a cramped quarter like that. So NASA's default is to bring large steel structures. Think if you've seen the series For All Mankind. So this is the traditional approach. You bring your spacecraft. The nominal Mars mission is now thinking about a 29,000 kilogram habitat to bring. So now you've got a huge upmass problem. But we think there is a better way. One approach is to take the regolith, the surface material, it's not normally called soil because there are no organics in it, and use that as a construction material, maybe making some kind of concrete or making ice houses. But we think there's even a better way. And so Chris Maurer, who I hope some of you met yesterday, principal architect of Red House Studios, my main partner in crime on this, had started to play with mycotecture and as a we to build a biodegradable drone. And so we both sort of simultaneously had the same idea of turning to fungal mycelia as a way to build actual habitats off planet. Now for the one person in the room who's never heard this before, the fruiting body of many fungi is called a mushroom. You're aware of that. It's densely packed mycelium. But the main part of the mushroom is actually these mycelial fibers that grow beneath the surface, more in a thread-like way instead of crunched into a mushroom. And so now you have these fibers that have evolved over X period of time to bind soils, among other things. And many of them really love rotting wood. And so why not take that ability and use that, again, to make a habitat? Again, we started off by using it to make the body of a drone. So you can do this by taking a mold and literally putting it in a mold and some wood chips or some other kind of material for them to eat. And my students have tried everything out of my pantry, from rice all the way to used coffee grounds. And by the way, they were fine on the used coffee grounds for about 8 days, and then they sort of spluttered out, and I can only think as a tea drinker that they over-caffeinated. That is not a scientific explanation, but whatever. Anyway, so we think that we can do this. And so this is, again, Chris's beautiful image here. We're now on our phase 3 NIAC, which is the NASA Innovative Advanced Concepts Program at NASA headquarters. It's a one program that funds work that's looking 10 to 30 years or more out. And obviously I have a very warm feeling about them because they've loved my project. So it's a mutual feeling. So these are the sort of far out NASA projects. So why should you even think about mycotecture? Myco being, from the Greek for fungi, and texture from the architecture, and so it's a portmanteau that I think Chris may have come up with mycotecture. Well, it's low mass, so you've started to take care of this up mass problem because you can grow it on site. So that cuts down the cost. And it's a great material, both for building, because you don't need to worry about joints. You can make anything into any conformation. And it's got great psychological properties. I don't know about you, I don't want to be in space for long periods of time and my entire environment is steel walls. It's adaptable to the site because you don't know what you're going to get. It's not like, there's construction crew there making, doing the excavating for you. Potentially self-healing because it's alive. Multiple other uses I'll show you in a moment. Sustainable and end of life, in principle, compostable. So I've started calling this green architecture for the red planet. And this is a paper that Martin's on, I think Rolando, you're on it too, and Jess. And this was, the lead author was Martin's my graduate student, Monica Lipinska, and we just compare a lot of these other options for growing off planet. And you don't really want to read it all, just suffice it to say, the stuff in green, our stuff, really comes out well. Chris lent me this picture to give you an idea of how really strong you can make mycelial composites. You can make a whole range of materials from these really strong ones you'll see in a second, all the way to mycelial foams, which we're working with someone who's pioneered that work in Alaska as a styrofoam substitute. But just watch this video. I just love this. And this is from Chris. You can see the mica texture on the right and concrete on the left. And guess which one made it? So, you know, I'm not someone in a planning department who approves, but to me, these pictures, you know, these movies say it all. Again, it's a tunable material so that you can make it in different conformations. Now, you can't just grow mycelium on the surface of the moon or Mars the way you can here, because there is no stable liquid water on either body. The problem is you basically have a vacuum, so by the time you combine the temperature and the pressure diagrams, you don't end up with liquid water. You can end up with a gaseous form, and you can end up with solid frozen water. So we're going to have to put these in some kind of protective structure where we can increase the pressure so they can have liquid water to breathe. So we're working with a company that specializes in inflatables for off-planet. And here's a little video that they made with Chris of a mock-up of an inflatable that we can use to grow our fungi in for a little habitat off-planet. By the way, that also takes care of, before someone asks about planetary protection and contaminating Mars, that also takes care of that. So here's a video that some of you may have seen in the exhibition that Chris put together. I'm going to show it anyway. Don't worry too much about the details, because if we're fortunate enough to ultimately have fungal habitats on Mars, I'm sure there'll be some changes. But this is sort of our vision that we are presenting to NASA, where we have this inflatable that's been already seeded with fungi and so on Earth. It gets water that's locally sourced. In my dream, we have these algae that are providing this interface with the raw materials on the planet. So the algae are now starting to grow and fill these little bioreactor cells that Chris is imagining here, made out of the inflatables. And then after they have filled those, we then activate the fungal mycelia that grow on and in and between the algal filaments, and you've ended up with a habitat. And I think there's a little bit more to the video. It takes you back out. And here we have it. I must have finally edited it. There's a picture at the end of a woman inside the habitat wearing a skirt with a handbag over her shoulder. It's like, I've got an imagination, but that's not happening with female astronauts on Mars. It's not going to happen. So I think I finally got sick of trying to explain that. Anyway, so we've done a lot of work trying to look at different fungal types and growth potential, and Chris has been under a lot of pressure to come up with architectural drawings, something that is so far out of my realm of expertise, you know, thank goodness. And I'll show Monica's work in a second. But phase 3, they want to actually see that you might have a customer. Now, for the NIAC, a customer is not necessarily a paying customer like the rest of you. We should be so lucky to get kind of seats money. So Starlab got one of them, Axiom got one, I forget the other. And what Starlab is doing is they want to provide both tourist and research facilities off-planet. Unlike a lot of the other space stations like ISS or Axiom, they're not being built in parts. They're building it as a single unit on the Earth and then launching them as single units. So that means it's easier for us to get involved. And so we had gotten the people who were the Ohio State leads for Starlab to come down to Chris's studio, I guess up to in Cleveland. And they got really excited, including the plate and the chopsticks, which I think you saw in the exhibit. Note, using chopsticks to eat sushi in microgravity is a really bad idea. I just gave a talk a few months ago at Food and Ingredients Europe, and it turns out the most popular thing to eat on ISS is actually tortilla. You can't have bread either because the crumbs become an inhalation hazard. So anyway, that's just a total aside that has nothing to do with anything. But they got really excited about the sort of materials that we could make, and so what we're working on is taking their plans for, here's one of the decks of Star Lab, which you can see is all very metal and sterile, and provide panels, which will provide the psychological benefit. It turns out they also have really good acoustical properties, and there's a lot of vibration on these space strips. And it also is really good for low flammability. There are a whole lot of reasons we want to go with microtexture. So take a look at that picture. Now imagine that we've got microtexture panels that we've been able to install before launch. Now it gets better than that. It turns out that there are fungi that produce melanin. Melanin is a series of compounds that a lot of organisms have figured out how to use. And in fact, assuming no one in the room is an albino, and I don't see any albinos, every one of us is producing melanin. That provides the color in your hair, that provides the color in your skin. Melanin is also available in a lot of fungi. Some of you, maybe most of you, and I won't name names or point out anyone, but many of you may have had some experience with heavily melanized fungi. Have you ever looked at that seal in your dishwasher and said, ick? This black stuff is heavily melanized fungi. Now, it turns out that we make the melanin to help protect us from ultraviolet radiation. But there's a lot of thought that melanin can also protect from ionizing radiation. And so here's some samples that probably Rolando was supervising that a graduate student at Stanford made, Kat Kornge. And you can see the one over on the left that doesn't have melanin added, and here are these black ones with melanin added. And what's really cool is that there are some, again, naturally melanin-producing fungi that would be perfect for our microtexture project. Now here's a picture of Brookhaven National Labs, and this is the space radiation facility for the United States. So if you really need to test something under space conditions, this is the gold standard, to go to Brookhaven and put it under one of their accelerator beams. And one of the members of our team, Radimus Cordera, who's a specialist in melanin, he's formed a company called Melitech, in fact, took some of our bricks, and you can see the one on the right, the number 2, is not heavily melanized. You saw ones like that up in the exhibit. Number 1 has a much more heavily melanized fungus in it. And then go ahead and look on the right at that graph. What you can see is that all the thickness of the 2 bricks was virtually identical. The transmission of this heavily ionized radiation was vastly different. That sample one with the melanin only let about 1% of the dose through. That's huge compared to the one that was not heavily melanized that basically left all the radiation through. So now you're in a position that you say, well, gosh, if we use heavily melanized fungi, maybe we can also protect us from ionizing radiation. Thus, we are starting to call some of these NIAC black in a shameless way to our funders. So now when Chris is starting to think about habitats and furniture for Star Lab and beyond, we're now starting to think of them using NIAC black, because now you've got some built-in ionizing radiation protection. And so, again, some animations that he made. Here is an astronaut going to bed. The astronauts today sort of buckle themselves in vertically, but you got paying customers over long periods of time. You might want a more sort of Earth familiar friendly situation. So Chris imagines these pods, and then you have this little pressure thing coming down so you don't float away during the night. Anyway, I love this idea. Anyway. And so I promised that I'd mention Monica's work. What she did for her PhD was focus less on the binding of wood chips and filaments and other sorts of things the way she started in my lab, but had focused more on making bricks and so on using sand. And that's part of the Northumbria exhibit, also at the exhibit space. And so these are some of the shapes that she played with. What I love is that some of them, I believe the idea was that you could have interlocking bricks, so you could almost toss them and have them interlock, which I love. Now, these were made with sand, but what we have done in the lab is taken Mars and lunar regolith simulant, because we don't have any of Mars in my lab or anywhere. Well, actually, we do have Mars on Earth, but we don't in my lab. But if you take the simulants and you add some nutrient solution, you find that the fungal mycelia grow just fine. So that gives us confidence that you could do a similar sort of thing with the surface material. So, so far I've talked about life as a material, or using life to make materials, for example, with the microtexture. So let's try looking at life to extract materials. So we've also looked very closely at the question of whether you could take advantage of this thing called life and use it for material extraction, particularly metals, and metal separation and bioremediation. And that sort of jumps to the punchline. But it should give you a little bit of the background, and that is that many of the proteins, over 50% of the proteins in your body, bind metals. Think of hemoglobin, for example, that binds iron. Now, it binds iron all the time, every day, or you would be dead. Your hemoglobin doesn't just wake up in the morning and say, gosh, wouldn't it be fun to do cobalt today, or selenium, or manganese sounds cool. It doesn't work that way. You wouldn't be here laughing if your hemoglobin did that. It's all the time, every day. So what if we can take advantage of that specificity? So what we've done in my lab is take short stretches of amino acids, so we call peptides, so parts of really very tiny proteins, that bind metals very specifically at one end of the protein. And the other end of these proteins, we put a binding site to bind the fungal mycelium. And now you've got a tunable filter that can bind any metal that you can find a peptide for. And we have a database that is remarkably good at covering the periodic table. It is top secret right now, but we do have a database that we found from the literature, and more peptides are being made bioinformatically every day. So we do have a paper on that. After much finagling with the US Patent Office, we finally got the patent issued on that. So we're really excited about it because, like the microtexture, if you're in the mining business, you now can grow a filter. You can grow anything you want to pull out the metals. You don't need a big manufacturing facility that makes, 2-meter flow through tangential ones, and you say, oh, that's great, but I needed one that was 1.5. It's like, oh, well, we don't have the, you can make anything. The fungi don't care. They'll grow to fill any mold. So I really love this because, again, the filter substrate is cheap, it's tunable, and, do anything you want, and then at the end of life, you can compost it. Now, it gets even better than that. This is wonderful postdoc at NYU, Simon Vecchione, started with me when he was an undergraduate at Brown, and he really wanted to build a radio transmitter with bacteria. And this was a while ago, and I looked at him and said, I couldn't build a radio transmitter with a kit from Radio Shack. And so we talked him down a bit off the ledge and ended up discovering something really interesting. And that is the DNA, which normally binds adenine to thymine and guanine to cytosine. If you have a cytosine-cytosine mismatch, so you don't have the binding in your DNA, you purposely put in a mismatch, that silver will very specifically go to fill that mismatch. And what you're seeing here is a cartoon of an NMR that he took, and it turns out there's actually 3 silver atoms for every mismatch. So you now have another way to do biomining, which is actually less susceptible to changes in pH. And also you have a way to make a wire. And that's why we're calling this biowire, because if you think about it, a wire is just this long, straight thing that conducts electricity. Now you've got a long, straight piece of DNA, again, cheap and easy to make, that you can put in conductive silver atoms exactly where you want them, so you can tune it. So he then went on for his PhD at Columbia with NASA funding to do all sorts of 3-dimensional DNA origami sorts of things and tiles, and he's continuing that sort of work as a postdoc at NYU. Really, really cool stuff. And he's got a bunch of papers and patents and all that sort of stuff. Now, we talked at the very beginning about this problem of having a gap, a communication gap, as well as a physical gap between Earth and your, for want of a better word, your construction sites off-world. The way to really get information quickly, having massless exploration is sending digital information to then make your biological materials. This sounds totally crazy. Every one of us is a continuous biological chain all the way back to the origin of life. There were no breaks. We may not be able to say that in the room in 20 years, but at this point, everyone in this room is descended from our last universal common ancestor. We are all related. But you don't need that physical continuity anymore for things like DNA or protein, or in fact, at this point, we can make a virus from scratch. Scary, isn't it? One thing we make from scratch is a virus. We can send that information. Our students do that all the time. They go to their computers, they come up with a DNA sequence, they hit send, I hit send on my credit card, and somehow this DNA is made. And it really doesn't matter whether it's made across town or across the world or on a different planet. You have broken that physical link. And so now you have all sorts of possibilities off planet there. What about chemistry? Biology has done chemistry for us throughout the history of the planet. I mean, we have a 21% oxygen atmosphere to breathe thanks to first the cyanobacteria and then the algae and then the, as former advisor of mine used to say, the big people plants. It also makes our sake and our beer and our bread and everything you eat is biologically made through chemistry. And this pretty much sums it up. I don't need to belabor the point. So why not use organisms to do chemistry off planet? You don't need to keep calling sigma when you're on Mars. You can make your own chemicals. Now, what happens as you're going to longer duration missions that you're farther away from Earth and you don't have that capability of aborting and getting back quickly when an astronaut gets sick? And this will happen at some point. Now, the problem is you cannot absolutely take everything. So we've come up with an idea of how to make an astropharmacy off planet. And yes, somehow we got on the cover of the Daily Star. and we're smart, and I don't know if I told you, the Star picked this up, and then the BBC picked it up from the Daily Star. I was under the impression it worked the other way. Silly me. Anyway, that's my big claim to fame. So here's our astropharmacy, again, a cast of 1,000. And we're doing this using microfluidics. Jess is involved and other people in the lab, where we're programming Bacillus subtilis spores, remember those little white dotty things I showed you at the beginning, to make drugs. So instead of having to worry about you not having the right drug or your drug expiring, because a lot of drugs, particularly biologics, expire in under 6 months, and that's with refrigeration. And shockingly, right now, the Artemis missions do not include a refrigerator. Who knew? So just forget any of those classes of drugs. But what if you could, again, program Bacillus subtilis, you add some culture medium when you need it, and they produce the drugs, and you do through a microfluidic system, purification, and within 24 hours, you can give these drugs to the astronaut. So that's what we're developing with this system. But we talked about Bacillus subtilis, but there are lots of other organisms in the world. And there's nothing, unfortunately, that will grow on the surface of the moon or Mars, and never will be because of the problem with the liquid water. But we certainly could push the bounds, which would cut down on the amount of energy or power we would need to grow things off planet. So what if, for example, things could grow at a higher temperature or a lower temperature and be more productive? So this is a project we've called the Hell Cell in my lab for since 2012. I love the name. Current postdoc keeps calling it synthetic extremophiles, but I mean, Hell Cell is much more vibrant. And so we have had this background of years of doing field work. This is in Yellowstone National Park. It was my daughter when she was about like 4. She now has her PhD, so it is a little bit old picture. But nonetheless, it gives you the point that you can go to these extreme environments and take out the capabilities to live at extremes and then put those into your production organisms. So again, something we've been working on. Or why not just make life de novo? Maybe what we've got with the lipids and the genetic code we have and so on isn't always going to work. And maybe we could make a life form that has a titanium shell, and that would be much better. Maybe it can't divide, but who cares? I'm not sure you need to have it divide every day. Some of you may know John Cumbers, who formed Syn BioBeta. He was a graduate student of mine. He kept saying, but you've got to have them divide, you've got to have them divide. And I said, look, John, if you're a chicken farmer, you don't want your chickens, your hens, to divide every night. You just want them to lay eggs. And I think it's the same situation here. Maybe you produce a titanium-coated cell that's really good at producing rubber. I don't care if it ever divides again, it just keeps producing rubber. So there are people, both in the astrobiology origin of life community, but also in the more applied science community, who are working very hard on building cells de novo. And this is a really interesting enterprise because we are at the point that we can take cells and we can put them in the blender and we can't put them back together. I mean, there's something about it, but yet there are people around the world who are doing incredible things, making lipid vesicles, which we've been doing at Ames for years, but then putting in systems where you can start to have transcription and translation and maybe making something interesting, including making, regenerating their own energy. And at what point when you're doing that, does it count as a living organism? And maybe it doesn't matter as long as it's producing the biomaterials that we need off planet. And maybe we, again, bioprint this and becomes all sorts of interesting things. So I've given you what I call the big ideas, sort of biology doing chemistry off Earth, sending digital information, the nanotechnology, which I didn't go into great detail, but you get the idea. Electricity, everyone in this room is converting chemical energy to electrical energy. If you, again, are still with us, this is something that we do all the time. It's just that electric eels are really good at storing that electric energy and then letting it go all at once. So yeah, you could do that. We can produce drugs on demand. Even I can. We can do biomining. We could make maybe life 1.5 or 2.0. And again, getting back to the idea of using organisms for material production. So this all sounds, marvelous, but maybe it's about time that we put our money where our mouth is and try these off planet. So as was mentioned earlier, we had this opportunity to fly a payload on a German satellite called Eucropus, which is really interesting because it flew at 3 different gravity regimes, depending upon how fast it was spinning. Again, the German Space Agency is the DLR, and we had the power cell payload, and what that was the first demonstration of synthetic biology of different gravity regimes, which worked very nicely. I won't go into the details, but the answer is the basic techniques of synthetic biology should be able to work in different gravity regimes. What about the microtexture? As I mentioned, we're working very hard to get on Starlab, but we also are trying to get on what's called Eclipse mission, which is the commercial lunar payload services. So there are various commercial entities that are providing services. None of them have actually done it successfully yet, but the idea is that NASA takes out contracts and DoD and so on, and they provide payload services to get the payloads to the surface of the moon and either deploy experiments inside of the spacecraft or a shelf that comes out or actually deployed to the surface of the moon. And so this is my vision of a little microtexture city growing on the surface of the moon. And I feel like this will be the mic drop of my career. People say, oh yeah, I do biomaterials. I say, oh, did you make a house on the moon? No. Bam. So then I'm out. I can sign off. So I'd like to finish with a few final thoughts. And that is that we have biological cycles on Earth that use these biomaterials that then degrade them, and then we make new biomaterials, and this works beautifully. We have a tech cycle on Earth that really isn't a cycle, it's a one-way at this point. With our biomining, we very much would like to be doing more recycling spent electronics, but right now we have a tendency to take, make, use, dispose, and pollute. When we come off planet, we now have this upmass issue. And so we've gotten really good at recycling water. The saying is, yesterday's coffee is tomorrow's coffee. I do not need to go into great detail what that means, but we are really good at water. We are not so good at a lot of other things. We send back, even laundry. I finally have extracted $70,000 to start to build laundry systems. They don't do laundry in space. They bring their spacesuits back that are really expensive. Their underwear and socks and so on, the polite word at NASA is it's deorbit it. So it burns up in the atmosphere. That's not a great way to do laundry. We finally, that's my Canada proposal. We finally did a calculation. If you had 6 astronauts changing clothes as often as they do on ISS, figuring 2.5-year round trip to Mars, it ends up with 2 metric tons of laundry. Even I, a biologist, could make a washing machine under 2 metric tons. This is something that's got to be solved. Some days I wonder, is anyone looking at these things? So anyway, we need to be able to recycle clothes. We need to be able to recycle the food. We need to be able to do all that because it is too expensive the way we're doing it now. And it's certainly not going to work as we get even farther. There is not a biological cycle on the moon. Is there going to be a tech cycle someday? Don't know. Is there a biological cycle on Mars today or ever? My astrobiology hat, I hope so. Don't know. But right now we do know that there are a lot of great resources that life needs, like these minerals and metals, and we've got the CO2 in the atmosphere. It's 95% CO2. It's just that the total pressure is much lower than the Earth. We even will have metals from spacecraft. I always say to the biomining community, the best place to find the materials to make a cell phone is from a dead cell phone. Why not recycle them? Again, there's water there, so there's all sorts of potential, and there is no existing industry we have to displace. All we have to do is get it to work, and then someone else can worry about how to make it less expensive for planet Earth and stuff. All I'm trying to do is see the future. And this again reminds you that our infrastructure on the Earth is very heavily based on petrochemical products. I got this from a website from the petrochemical industry. They're really proud of the fact that everything's made in petrochemicals. I look at this and find it terrifying. So it gives you a roadmap to what you got to get around. So are we someday going to have a tech cycle on Mars that's like this? I certainly hope so. We would love to. I'd love to be part of that. So I've given you all these constraints that perhaps you've not thought about before because you're not in the off-planet biz. And you've got other kinds of constraints that you need to worry about. You've got your investors and, scale up and all those sorts of things. And I'm sitting here worrying about up mass and up volume and storage and reliability and flexibility and where every carbon atom's coming from and every water molecule and so on. But do I look depressed? No, I'm not depressed. This is my 4th lecture this week and I'm still not depressed. No, because I firmly believe that these constraints actually unleash creativity. And being a scientist is a highly creative enterprise if you're a decent scientist. And because of these constraints forcing this kind of creativity, I really believe that we will end up with game-changing solutions that are going to revolutionize space infrastructure with its radical sustainability, but also provide the solutions for planet Earth in the end. And so with that, I say ad astra, which means to the stars, and thank the many people who are in my lab now and have been in the lab, and the iGEM teams who pioneered a lot of this, including the mica detection, the astropharmacy, and the biodegradable drone, and the biowires. The ones in blue are ones that are currently incarcerated in my lab are with me, and I hope that they're with me forever because we really have a fabulous, fabulous team. So thank you so much for your attention. I realize this was pretty much off topic, but I hope you enjoyed it and got you thinking about some of the novel uses of biomaterials. Thanks so much.
Let's open it up for questions. Who's got questions? What a cool presentation and enthusiasm. Any hot takers? I love at the end, because one of the things I struggle with space is always about but I'm here on Earth. And I loved your final slide about game-changing with space change. What are the areas that you've seen either recent or you have hope for that through your research or colleagues' research will change for the Earth-based? Is
Well, again, the biomaterials, obviously, I know there are a lot of people in architecture here. So he mentioned I've spent the last 3 days with the mining industry. And it is radically different than what people do in mining today. The toxic tailings is a huge problem, spent electronics is, and I was just thrilled that we got the response yesterday that we did to these ideas. It's incredible to me that we've done this, and thanks at this point to Rolando, who's really moving us forward on, like pennies. I know we don't have pennies anymore as of last week, but you know what I mean, because it really is, I think that is something alone that will revolutionize. And you think about it, metals are really important, and yet they are not uniformly distributed over the face of the world. But because we already have the electronics and so on, I think the ability to recycle them will be a game changer, not just for the environment, not just for industry, but geopolitically as well. So I'm really bullish on that. I think the pharmaceuticals, the application is personalized medicine on demand. We started talking to Merck when we were starting with the pharmaceuticals, and I discovered that an orphan drug is a drug that in the United States has fewer than 20,000 people who need it. 20,000 is a lot of sick people. But we're sitting here with this, radical individuality with a little tiny microfluidic device able to make something experimental without having to gear up to a huge facility. So I think that ultimately that could also really save lives. I'm trying to think what else we're bullish about. So with perchlorate detoxification, that's not a huge problem on the earth, but there are spills of perchlorates that can be a problem. The reason we are focused on that right now is because Martian water is contaminated with perchlorates. So we have no choice with Martian water, but there are occasionally big toxic spills, including from the aircraft industry. We're starting to play around with trying to get some biomaterials into aviation, because we feel that's also ripe. I've stayed away from biofuels because there is already industrial interest, and being a government worker, we're supposed to stay away from competing with industry. But Rolando, Jess, and I, among others, are starting to think about ways that we could literally inject biological materials into spacecraft so that you can end up with this thing that they now call sustainable aviation, or green aviation. So those are some of the things that, right now I'm bullish about, but, I love everything. It's sort of like asking what my favorite one is. And what my greatest fear is, after all these ideas and doing, the other sort of part of my life that I love, that someday when I'm dead and gone, the only thing people are going to remember me for is laundry. That is my greatest fear.
Hey, well, we all need it. Does anybody else from the audience have questions?
First of all, beautiful presentation. Congratulations. I love it.
Did it all last night.
Yeah. So I was curious about, you will need tons of substrate or nutrients to grow out the city,
Yeah.
all the fungus and stuff. It's heavy, all the nutrients you will need. How do you think that they will fix that issue? It's a lot of mess.
So, do you want to take that, Rolando, or do you want me to? You can. Your turn.
Was the question for Lunar or
For the project that you have, the gel,
Great answer.
the gel that you're going to build with the fungus for the labs that you will
a couple
have.
of things. So you're all familiar probably with SpaceX and other commercial providers that are trying to get the launch cost down to somewhere around $1,000 per kilo, $100 per kilo. There's other systems that are now, you can look up a company, a startup called Slingshot, that is trying to develop a railgun to basically shoot big bullets full of stuff. You'll send people on, you can't send people on a bullet, but you'll send stuff that people need, and their tagline is something like trying to be the UPS of space. So we aren't just launching things and rockets, but we have big rockets, and those big rockets will carry a lot of stuff, and we could probably pack up. We're developing that right now and figuring out how to fold up, as you see in the video, how to fold up these systems, and we can lyophilize these organisms, which means basically like freeze dry them, and we come in kind of suspended animation. When we get there, we have the rover or other robotic systems that would, again, these things would land first and start to do this kind of mining and sourcing of materials, and we send people after it. So a lot of this stuff would start to be incubated and grown before we get there.
To summarize what you're saying, a lot of what you're talking about is of the mass. I mean, it's not weight because that has the gravity vector, but if you want to think of it as weight, is water. We're mostly water. I actually found out, men have more water, are more watery than women because of the fat distribution. I had that statistic or something. Anyway, be that as it may, a lot of the mass of biological materials is water. So if you're getting the water from off planet, you get around that. You get culture medium powdered. That's how we get it. We don't get it liquid. We get it powdered, and then we have water. So, thank you.
Thank you.
I have a question.
Mike is Margaret.
Okay. One of our students, Claire, in Jason's class, was talking about composting bodies for,
Yeah, see with it.
yes. And so I wonder if you've been thinking about that when people die in space. Can they actually go back into the life cycle and create food?
My gut reaction is NASA does not want to talk about that. I think that, they don't want to talk about people dying off planet. I think the feeling at this point would be that you would bring the body back and bury it in Arlington. That being said, Elon Musk is on record as saying that he wanted to die on Mars, which was ultimately changed to not on impact. I don't know if that is still his current plan or not, but he did say that at one point. So I'm sure he might want to buy one.
Sooner the better.
I only leave it out there.
When Andy asked the question about applications here on Earth, because I will say, incredible talk, but when I hear it, maybe because it's coming out of sort of people's mouths, I feel a little bit more crystallize a little bit, but we're thoroughly trashing this planet. And there's work we can do here that's probably much less expensive than terraforming other planets. But there's so many things that you're doing that clearly have immediate applications here, and I'm curious about the economies of those applications. So I would imagine that pharmaceutical companies don't want you delivering the tools to individuals to manufacture their own drugs.
Well, interestingly enough, they've said if you're able to develop something, we'd be really interested because I'm not going to spin off a company. I can't as a civil servant. So what we want to do is patent and then have them lease it and make the money. That's fine. They can make the money. But where I thought you were going with this is often a question of why do we spend money on space?
Well, no, I mean the applications, that broad applications for the things that you're focused on because of the parameters of space and food source. I mean, NASA has always created things that come back to Earth for benefits, right?
Absolutely. But we do often get the question, then why not just spend it on feeding people on the Earth? And what I'm trying to make the point is that we don't. We have the money to feed everyone on the Earth. It's a political problem. It's not my problem. NASA, unlike what a lot of people think, we get 0.05% or 0.5% of the federal budget. It's nothing. And most of that's going to the big aerospace contractors. So you can zero out NASA and that would not feed the world. But what it does do is two things. Three actually. The politically correct thing is that it provides spin-offs and for people on Earth. The not so politically correct thing, which is clear from Sputnik on, is that it provides us an opportunity to have a soft show of power, technological superiority. Sputnik and I are we're well aware of Sputnik. But the third thing that as I get older, I've become increasingly aware of going around the world, and particularly having gone into schools in Kenya. And these range from schools that were very elite private schools in Nairobi to ones in the slums of Nairobi where these kids had nothing. And yet, in fact, I went in on a day that was a holiday. A lot of these kids were orphans. The place it was like a one-room schoolhouse up to about 16. The classrooms, quite honestly, smelled of urine. There was corrugated steel on the roof, and you could barely hear when it started raining. Yet these kids were at least bilingual, and I think some of them were trilingual. And this place was packed when we showed up to talk about space. Not because they were getting credit, not because they were getting food, but it's because we as humans are explorers. This speaks to something that is part of being human. We are not well-fed cows. We are humans. And so I think we have no choice but to explore because that's built into our very being.
Heading in that direction.
Well, I've taken care of it, just in case.
So many of the things that you share, when we think about applications here, they're almost like a DIY. They could get to that level, it seems to me.
Absolutely.
Right? So that's why I asked a question about the economies of that kind of application.
Yeah, no, we could. Rolando thinks about economy, and I, in spite of the fact I had the name Rothchild, it was inherited. I didn't earn it, and so I sort of stay away from that side of it. You know, I'm the idea person, and this could change the world, and someone else is going to have to worry about, doing the financing.
What a great finale of that answer. Thank you for sharing this.
Thank you.
It's on.
Incredible talk, thank you so much. And I was really taken by the image that you showed, and I can only describe it as the new primitive hut. We're mostly architects and designers in this room, and there's this notion of how the origins of architecture. You showed this, it was a bone, a mammoth kind of construction, which really got me really thinking. And I guess I'm curious about in your talk, in terms of the representations you're showing of the kind of pioneering habitat that might be on Mars. And I'm kind of disappointed in a way that it feels like a technology. It doesn't feel like mycelium growth or something that's biological. It seems very top down, and I'm wondering what the habitat would be when humans wanted to build a community and wanted to do more than just explore. They wanted to settle, and they wanted to build, and they wanted to have a poetic life on another planet, and what that would start to look like, and the limitations of some of the representations that you're showing.
You mean like having walls and privacy
Right.
and all
I mean,
that
you
sort of stuff?
hinted at this notion that we could begin to build from within, and these building blocks and customizable and these kinds of things. I am kind of curious about the roots of some of this in science fiction and other things, and we're like sort of this technological imperative, kind of building up the dream of 2001: Space Odyssey and all of the nightmares of that instilled. But you're so optimistic, and you're sort of pitching this amazing future. But I'm wondering about sort of community, and I'm wondering about cities, and I'm wondering about civilization and art and culture and communication and love. And you have sort of
These are really great,
what
great
is
points.
in it
And
for
yeah.
society, beyond
Yeah.
the technological imperative that we're
I will say one thing bluntly is we're not going to get to any of that until we solve the problem of living in low gravity. We're going to have some kind of medication, more likely some kind of centrifuge, because it is really hard on the human body. Your vision goes, your mental facilities go, and that's, in addition to the fluid flow changes in your stomach and everything else. So it is so hard on the human body. So right now, the idea of long-term settlements in these places is insane. If everyone spends their hour a day in a centrifuge and that works okay, then we can start to talk about that. I think all these things you bring up are fabulous. As I say at this point when the program review, I can't solve all of life's problems. but I'm hoping by putting these out that, you know, people like you will then go the next step, and that would be incredibly cool. One sort of trivial though comment, we started with some of this by doing biocementation, making bricks. And so I used to show all these pictures that they took around the world of buildings made of bricks. New York's made of bricks. I mean, you know, you can make churches, administration buildings, you can make anything out of bricks. And so what if you start to make, you know, bricks out of the regolith, either, you know, fungal or whatever, then you have this flexibility to build everything. Whereas with the, you know, with the inflatable, we're thinking of a single one. However, I've also suggested to Chris that we do a sort of a bubble wrap situation where we have little tiny bubbles of mycelia. I mean, imagine you had a roll and then you could pull it off and you drape it over something and you add water and you grow a table or you grow a chair that way from sheets. And so that's as far as I've gotten on thinking of how you could customize on demand. But again, everything you bring up is a really great point, and I just haven't gotten any further than this.
There's a really, you know, I'm trained as an architect, so I'm thinking from that end, but there's a really incredible project by an architect named Frederick Kiesler, who built it's called the Endless House. And there's crazy images of him in a museum inside the house, which he was building live in a way, in situ, and actually building the house from the inside out, using, I believe, plaster on like chicken wire at that point. But it's a really different model in a way, and it's something that would be interesting to sort of think about. Right?
Yeah, no, this is great. I'd love to follow up with you on this.
Thank you.
All I can think is IKEA. You know. Give them a run for their money. Anybody else?
Fun Kia.
Yeah.
Sorry, yeah. So I have a crazy idea, maybe doesn't make any sense, but I
Can't be any crazier than our ideas.
I was thinking of the cows taking our bioreactors. Can we, I mean, you need, in order to grow your biomaterials, you need acids. You need to grow the bioreactor. But bioreactors are huge and they have, you know, all this kind of,
So I don't know if you noticed, right, in that animation that I showed you that Chris put together of the house, each of those cells on the ceiling, you know, around the surface was a little bioreactor. So a bioreactor doesn't have to be a big glass or metallic thing. It can be, the bioreactor can be in an inflatable. And that's one of the things that we've been looking at. So, yeah, it's just a different idea of a bioreactor.
You got a follow?
You know, once before, I gave a talk to a student group at the University of Michigan on Valentine's Day. And I think at this point in the talk, I said, don't any of you have dates? Seriously, you don't have to listen to me all night. Surely you have fun things to do.
One last question.
Okay.
My question is whether or not you think feasibly in our lifetime we'll see a habitat actually be built on another planet.
Oh, absolutely. I mean, you know, I shouldn't have fate. I could get hit by a truck tonight. But no, there's no question there'll be habitats built. Now, what they're going to be made out of is the issue. And if I'm going to be brutally honest, what we're doing is playing with seeing how far you can push biomaterials, and particularly the fungal ones. But it's sort of, I mean, when you build a house, and I feel silly even pointing this out to a room full of architects, but you don't have a client come to you and say, I want one 100% stone. You say, ooh, you want the water pipes out of stone, and the ceiling out of stone, and the walls? Yep, 100% stone. Of course you're not going to have 100% stone or brick or wood or whatever. You use different materials for different things. So if at the end of the day, what we've done with all this work on the architecture is gotten NASA to add this to their palette of materials, architecture word, then I am happy.
Okay, let's give.
Thank you, Lynn. A final thanks to the team that organized basis. I won't rattle off their names again, but they're here in front of you and everyone has met them by this point. And thanks to our students and alumni who have worked with them, our staff and students who made these 2 days happen, made that exhibition happen, behind the scenes, in front of the cameras, making things, making relationships, like just so many people were involved in making this happen. All of our participants, our new friends, new partners, hopefully in collaborations between CCA and all the amazing institutions at which you all are working. I will extend again an invitation to anyone in the room. If you are excited about something you saw in that gallery or something you heard today, get in touch with me, get in touch with Margaret, Evan, Alex, Nagar, Jason, anyone at CCA. Like, we are excited to work with people, like ideas developed through conversations and through different people bringing their experience together with other people to make things happen. So again, thank you so much for coming. Have a great evening and come back and see us again. We've got great lectures across the rest of the day.